The potential of 3D printing in space represents a paradigm shift in how we approach space exploration and off-Earth manufacturing. This technology, also known as additive manufacturing, allows for the creation of objects directly from digital models, building them layer by layer. In the unique environment of space, 3D printing offers numerous advantages and opportunities that could significantly enhance the efficiency and feasibility of long-duration space missions. One of the primary benefits of 3D printing in space is the reduction of launch costs. Currently, all materials, tools, and components needed for space missions must be launched from Earth, a process that is incredibly costly due to the energy required to escape Earth's gravity. 3D printing in space allows for the production of necessary items directly in orbit or on other celestial bodies, reducing the need to launch heavy and bulky payloads. In-situ resource utilization, ISRU, is a concept closely related to 3D printing in space. ISRU involves using local materials, such as lunar regolith or Martian soil, to create structures, tools, and other necessary items. This approach not only reduces launch costs but also enables more sustainable and longer-term missions. For instance, 3D printers could use moon dust to create habitats or bases on the lunar surface, a crucial capability for future moon colonization efforts. Another significant advantage of 3D printing in space is the ability to create customized tools and components on demand. This capability is invaluable for long-duration missions, where it is impossible to anticipate and pack every potential tool or spare part needed. Astronauts could simply print what they need when they need it, allowing for greater flexibility and self-sufficiency in space. 3D printing also enables the manufacturing of complex structures that would be impossible or prohibitively expensive to produce using traditional methods. In the microgravity environment of space, the constraints of traditional manufacturing processes are lifted, allowing for the creation of intricate structures without the need for support material. This capability opens up new possibilities in terms of design and functionality, which could be applied to everything from spacecraft components to scientific instruments. The International Space Station, ISS, has already begun to explore the capabilities of 3D printing in space. A 3D printer was installed on the ISS in 2014, and since then, it has been used to print various items, including tools and parts. This experiment has provided valuable insights into how 3D printing works in microgravity and its potential applications for future space missions. Bioprinting, a subset of 3D printing, is another area with tremendous potential in space exploration. Bioprinting involves creating tissue and potentially organs using biological materials. In space, where access to medical treatment is limited, bioprinting could be a game changer, providing the ability to treat astronauts' medical issues on long-duration missions. The potential of 3D printing in space extends beyond practical applications to potential economic benefits. The ability to manufacture in space could lead to new industries and business models, such as space-based factories producing high-value materials that benefit from microgravity's unique properties. These materials could then be sent back to Earth or used in the construction of space structures. 3D printing technology in space is still in its infancy, and there are challenges to overcome. These include the need to develop printers and materials that can function effectively in the harsh conditions of space, including extreme temperatures, vacuum, and radiation. Furthermore, the fine particles produced during the 3D printing process pose a potential risk in the enclosed environment of a spacecraft or space habitat, requiring careful containment and filtration. The development of large-scale 3D printing could revolutionize the construction of space habitats and infrastructures. Traditional methods of constructing space habitats involve transporting prefabricated modules and assembling them in space, a costly and logistically complex process. 3D printing offers an alternative by enabling the on-site construction of habitats using local materials. This approach not only reduces launch costs but also allows for more flexibility in design. Habitats could be tailored to specific environmental conditions or mission requirements, and structures could be easily modified or expanded as needed. 3D printing is also poised to play a crucial role in the creation of interplanetary spacecraft. Future deep space missions, such as those to Mars or asteroids, will require spacecraft with capabilities beyond current designs. 3D printing allows for the manufacturing of parts with optimized designs for weight, strength, and efficiency, which is crucial for long-duration missions where every kilogram of weight adds significantly to the mission cost. The field of robotics and autonomous systems intersects with 3D printing in space, offering the potential for fully automated construction and manufacturing processes. Robotic 3D printers could be deployed to extraterrestrial bodies to begin constructing bases or infrastructure before human arrival, significantly reducing the risks and costs associated with manned missions. These robotic systems could also be used for ongoing maintenance and expansion of habitats and facilities. In addition to inorganic materials, 3D printing in space also encompasses the use of organic materials, opening up possibilities in areas such as food production and life support systems. 3D printed food, using bioinks made from proteins and nutrients, could provide a sustainable and diverse food source for astronauts on long missions. Similarly, 3D printing could be used to create components of life support systems, such as filters or bioreactors, on demand. The space environment presents unique challenges to 3D printing, which must be overcome to fully realize its potential. Microgravity affects the behavior of materials, including how they flow and solidify, which can impact the quality and integrity of 3D printed objects. The vacuum of space and exposure to cosmic radiation also pose challenges for both the printing process and the durability of printed materials. Research and development efforts are focused on adapting 3D printing technologies to these unique conditions, including the development of new materials and printing methods. The regulatory and legal framework for 3D printing in space is another area that requires attention. As with other aspects of space exploration, the use of local resources for 3D printing raises questions about ownership and rights under international space law. The Outer Space Treaty, which governs the activities of nations in space, does not specifically address the use of extraterrestrial resources. Developing a clear legal framework is essential for commercial and governmental entities to invest in 3D printing technologies for space applications. Environmental considerations are also important, particularly in terms of managing waste from 3D printing processes. Ensuring that 3D printing in space is sustainable and does not contribute to the problem of space debris is crucial. This includes the development of recycling processes to reuse materials and minimize waste. In summary, the potential of 3D printing in space is vast, offering revolutionary approaches to building and manufacturing for space exploration. It holds the promise of making space missions more sustainable, cost-effective, and flexible, significantly advancing our capabilities for long-duration space exploration and settlement. The continued advancement of 3D printing technology, combined with research into its application in the space environment, is key to unlocking these possibilities and pushing the boundaries of what is achievable in space exploration.